Assalamu alaikum wa rahmatullahi wa barakatuh. So we are still in uh, lecture number 15. We are still in lecture number 15, and the last part of this lecture is talking about the two-level NAND and the two-level NOR. How can I achieve all the three optimizations together? Okay, if I can make the circuit um, implemented using two-level, and it is all NAND, all or NOR, and this simplification or implementation of the circuit coming from the K-map, that means I achieved the minimum area, the minimum delay, and one type of logic. So this third part of lecture number 15 will be about the two-level NAND and the two-level NOR. In the last two lectures, and including the re-lecture in the class, we have actually come up with the table that actually convert the different basic logic gates, the AND and the OR, how to convert them to an AND or NOR. So just to review, in order to convert an AND to an AND, I need a NAND followed by an inverter. While if I need the conversion from AND to a NOR, I need a NOR and two inverters at the inputs. The vice versa for the OR. If I have an OR and I went to implementation using NAND, I have a NAND and the two inverters at the input. If I have an OR and I want a NOR implementation, I have to implement that using a NOR followed by an inverter. Using this table, we still use the exact same table to achieve the last thing, which is the total optimization, through which I will have the circuit is achieving all the goals that we need. In order, and this is what we call what? The two-level NAND and the two-level NOR. So I can either achieve a two-level NAND or a two-level NOR. And the condition here is that the equation itself of the Boolean algebra equation, or the function that I have, should be one of the standards. It could be either SOP or POS, as we learned in the previous lectures. So, if this is the case, you can achieve two-level NAND and two-level NOR. So let's separate this. First, two-level NAND. The condition to achieve two-level NAND is that the equation, the Boolean algebra equation that you have, should be in the standard SOP. So, if you are starting with an equation that is in SOP standard, that means you can have the circuit as a two-level NAND. Example. So, here an example. Now, let's pick any example of a Boolean algebra equation. Let's say f of x, y, and z equals to, pick anything, okay? But the only condition is to be SOP. X bar y, x, y, z bar, maybe z, anything. Whatever function that you have. Okay, if the function is in SOP, that means it is guaranteed automatically that you can implement the circuit using two-level NAND. Right. How can I apply that, or how can I achieve that? I can simply achieve that by simply doing the exact same technique that we have learned before. Through this table, I can do the achievement. Okay, so let's this time draw the circuit in a standard way. all of us know how to draw this circuit as a standard. In a standard way, I have the inputs are vertical wires, okay? Two wires representing each parameter. This is the standard drawing of the circuit. Now, let's put the labels for, so I have here X, that means this line is X, this is X bar. Y, this is Y bar. Z, this is Z bar. Okay? So I will draw the circuit as it is. So in a standard way, I have two levels. One level for the AND and one for the OR. That means here I need an AND gate for the first term. This term is actually connecting X bar, so I have to take a wire from X bar and Z, and here is my Z. Okay. So this will give me an X bar Y. Second term here is another AND gate, connecting what? Connecting X, here is X, with Y, this is Y, with Z bar, this is Z bar. So the term here is actually X, Y, Z bar. Finally, I need Z. So I have here the line for Z. Then those three terms are connected through an OR gate. So I have OR gate here connecting those to give me the function F. This implementation, which we call it an AND OR implementation of the circuit, or SOP implementation, another name, or two-level implementation. This is two-level and OR implementation. This is two levels because any pass from the inputs here will encounter a delay of 2 tau delay for the two gates. Now, okay, how can I achieve a two-level NAND? Using the same concept. All what I have to do is to remove the AND, replace it with, replacing the AND with a NAND. Replacing the AND with a NAND means a NAND and an inverter and the wire. Correct? Then I have an OR, as we demonstrated in the lecture, the two previous lectures. So I have to remove the OR gate, and for the OR, I have to remove it and put an NAND gate and the inverters at the inputs. Correct? Now, I will just make the cancellations. Two inverters at this wire cancel each other. So those two inverters will cancel each other. Those two inverters will cancel each other. I have this inverter means instead of being connected to Z, I want to be connected to Z bar. So I will remove this connection and I will replace it with a connection with Z bar. So now I have the freedom to remove this inverter. This inverter has been cancelled by this. This inverter has been cancelled by this. What can you see here on the board right now? Now I automatically converted the function from and or implementation to two-level NAND. I have nothing in the circuit except the NAND. We mentioned before that inverters and inputs are we can NAND them. Now the circuit is two-level NAND. The only condition to do that is that the equation should be in SOP. Okay? This problem can be also shown how it is being implemented or how it is being achieved through what? Through the Boolean algebra. The Boolean algebra, I have the equation for f. How can I achieve this? So now we do it on the drawing. We can also do that on the Boolean algebra. Okay? So the equation for f is telling me that f of x, y, and z equals to x bar y or y bar z or z. Okay? How can I achieve two-level NAND on the equation? Simply putting 2 bars for the whole equation. And I will break the inner. I will break the inner. So accordingly, we will have the equation. If I put 2 bars and only break the inner, I will get what? I will get the first term, x bar y bar, breaking only the inner. Dot, when I break using De Morgan, I'm changing the operator from OR to AND. So x, y, z bar. And finally, z bar. Remember that I put 2 bars because I don't want to change the function. I want to keep the function as it is. So the function right now is converted to the following equation. This equation is exactly what we did on the drawing here. This equation, you can recognize that you have here, this is a NAND, which is the first NAND here. This is actually the first NAND. Then another NAND, which is this one. And the last term here is just one term connected to Z bar. Okay? One literal. Those 3 terms that are NAND are connected together through what? Through another big NAND connecting them together. So actually, I have here 2-level NAND circuit. Again, using the exact same table. Okay? But this is just achieved. Okay? Fine. Then the condition to achieve 2-level NAND is that the equation should be originally in the SOP standard. If you are about to achieve the 3 optimizations, 2-level NAND, and which means the one type of logic, the minimum delay, which is 2-level, and the simplest equation, that means one step needs to be added here. You need this equation first to be simplified using KMAP to get the minimum SOP. Okay? If you have the minimum SOP, put 2 bars, break the inner, you get 2-level NAND. So you achieve the 3 optimizations of the circuit. Okay? Agree? Fine. Now, how can I do the opposite? How can I achieve 2-level NOR? Exactly the same work. Nothing is different. Okay? You will do similar work to what you have just done right now, but for what? The condition is different. We have a condition that the equation should be in the minimum or be in the standard SOP. If I want to achieve 2-level NOR, 2-level can only be achieved if the equation is in the POS standard. Okay? So if the equation in POS standard, I can get the two-level NOR directly. How? Let's see an example. Another function, let's call it S of X, Y, and Z. Okay? Now, let's put some equation for this. Y or Z bar, X or Y bar or Z. Then I have here maybe X bar. This function S is in any standard? Yes. Which standard is this? This is SOP standard. Since the equation in SOP standard, that means I can achieve two-level NOR simply by doing the exacting same technique. We did it in the last lecture through the drawing. Okay. Now let's start by the Boolean. Okay. Can I use the Boolean algebra here? Yes. Y or Z bar, X or Y bar or Z, then X bar. The game is very simple. Put two bars on the whole equation. Did I change anything in the function? I didn't change anything. I put two bars. I keep the logic as it is. Then take the inner using De Morgan. Break the inner, so the first term will be Y or Z bar, bar. Then the operator will change from AND to OR. X or Y bar, all bar, or X bar bar. Don't forget that we have another bar to keep the logic as it is. So right now, can you see the two-level NOR? Yes, this is a NOR gate between Y and Z bar. This is a NOR gate between X, Y bar, and Z. And this is all one term connected to one literal connected to X. So if I have a NOR between those, NOR, and this is one term, what type of logic that you can see connecting all of those terms together? It is one NOR gate. One NOR gate. Okay? So can we see the implementation for this? Exactly as we did in the previous example. Here I have the three inputs. I have here X, I have Y, I have Z. The lines here give me X bar, Y bar, Z bar. So I will implement this. The first one is a NOR gate. You see this NOR gate? It's a NOR gate connecting Y with Z bar. This is a branch for Y. This is a branch for Z bar. This will give me what? Will give me Y or Z bar complement, which is the NOR. Next term here is another NOR gate. This NOR gate is connecting X with Y bar with Z. So the term here is X or Y bar or Z or 2 bar. Finally, I need the input X. What is the relationship between the output of this NOR, and the X? These are all should be connected to a one big fat NOR gate to give me the function S. Okay, so right now the circuit that we have drawn here is said to be two-level NOR. Agree? Make sense? So now we have finished the NAND and the NOR, and what's the multi-level NAND and what's the multi-level NOR. And one thing left for us for chapter 3, which is actually the one extra logic gate, which is that XOR to finish lecture, the next lecture. Now we finished lecture number 15, and we will go in our next lecture, which is lecture number 16, to finish the chapter number 3. Thank you.